Hey, hello, workshop friends, 121 workshop friends in particular. Hey, I got this question by email, so I thought I'd answer it with a video and then send it to the rest of you guys. And it's a question about velocity and time graph. I think you know it, and I'm going to just kind of read it here. I got it on my screen. Like I said, it was emailed to me. And so I'm just going to write out the title. It just says here that during her part of a relay race, a sprinter runs a total distance of 35.4 meters. Now, she begins with a speed of v1, accelerates at a constant rate of 1.49 meters per second squared for a time of 1.92 seconds. Then she reaches a maximum speed of v2, and she maintains that speed. Maintained that speed for a time of 2.95 seconds. All right, then they give this nice little picture. And so let me give you two ways to solve this. The first one is more of a graphical method, and I think that's what is wanted out of this problem. But the other one is we could do a calculations from it without ever having the graph. So let's maybe do both here. All right, and let me just kind of draw the graph. The graph is a velocity versus time. That's why it says velocity versus time graph. And it starts with some beginning speed, which they say is v1. Accelerates at a constant rate until they get to a speed of v2. She keeps that until she finishes the race. And so this would be a graph of her speed. Now, I think the intent, since they're giving you a graph, is to make sure you understand a little bit more about graphs here. So let me just connect graphs and mathematics together here. Because we know this. We know that the velocity is the rate at which the position changes with time. Okay. So the reverse of this, if you had this calculus problem and you asked to solve for position, you would move the dt to the other side. Then you would integrate. And when you integrated dx, you would get just x. And so what you're saying here is that velocity, of course, is connected to position. And if you think of it in its differential form, you get this. But if you think of its integral form, you get this. Now, here's why I say that. If we had a plot of position versus time, and let's just say it went like blah, you, I think, know from your calculus class that the derivative is graphically the slope at that point. So looking at a graph of position versus time, you could get its velocity from its slope. But what I want to show you is we don't have a graph here of position versus time. We have a graph of velocity versus time. Okay. And this is saying that velocity, the integral of velocity over time, gives you the position. Okay. What that means is the area under the curve. And I think this problem is helping you out by looking at a little color code here. And let me just maybe make this a little more solid so it stands out, because this is actually the graph. Okay. But by them making down here a rectangle and another rectangle and a triangle and looking at this, we know then that this area under here is the total distance that she moves. And that's the key really to this problem. We have a couple of other things that I guess we can kind of work out in all of this, but let me just, begin by saying this is, I think what this problem is all about is getting you to recognize that it is this area under here. And so let's manipulate it that way. But as long as I'm talking about graphs, let me also then point out that the acceleration is the derivative of the velocity, okay? So just like I was saying right here, if you had a graph of position versus time, the slope of that would give you the velocity. This is saying that if you had a graph of velocity and time, which we do, right? Then the slope of it would give you the acceleration. So did you notice that this had the same slope, right? They said in the problem that you had a constant acceleration, and the number they gave you was the 1.49. So what I'm saying here is even if I didn't even see this graph, I would know that it would be a straight line. I know that it would be a slope. And if they say it's a constant value, that means it's a constant slope. And that's the definition of a line, a constant slope. Okay. And then more than that, they say that in the latter part of the race here, it says she maintains this constant speed of v2. Now, if she maintains it, that means her derivative is 0. She has no acceleration. She's not going faster. She's not going slower. And if we translate that to a graph, that means the slope would be 0. And so that's why this is a horizontal line, right? That's what a slope of 0 represents. So know that the slope here is 1.49. And the slope here, if it matters, is 0. Okay? And so we have some information from all of that. Okay, so like I said, I think, and I'm going to show you two ways, but I'm going to do the way that I think the author is kind of getting at here, is the author wants you to kind of recognize this little fact right here, that position is the integration of velocity. Don't actually do the math, but know that this is the fact, and then look at the graph and get the area under it. Now, the second way I want to show you is I actually want to just do this mathematics. I want to do this integration, and even these integrations have already been done. So that's where we got those 4 kinematic equations, or maybe just 2 kinematic equations, or 3, depending on how many you memorized here. Let's see, the OpenStax lists it at 3. But we could solve all these with numbers and equations. We don't even have to look at this graph here. But nonetheless, let me build up to that. Okay. So I'm going to approach this. Maybe I'll just leave the picture here. Sorry, I was going to go to page 2. I'll label page 2. Okay, but let me stay here on page 1 for a second, because they tell us this time. So down here is 1.92. Okay. Let me just double check that. It says she begins her speed with some speed v1. So we don't know what that is. And she accelerates at a rate of 1.49 for a time of 1.92 seconds. So this is 1.29 seconds. Okay. Then she reaches a maximum speed of v2 and maintains that speed for a time of 2.95 seconds. Okay, so we know the 2 times here. Okay. Now, here's another interesting piece of this. Is we actually then would know what this height is, right? If we do it in terms of math, the slope is the rise over the run. See, this is the rise. I know the run. I know the slope. I can find that. Or put it another way, this would be saying that this is the change in the velocity would be acceleration times time. But maybe I'm getting too much into the math. I will do that soon. But let me just then look at the math here, and then, maybe come down to maybe this part of my page. So slope is equal to the rise over the run. Okay, so the slope is the acceleration, And the run is the time. And this would be the rise. And if I move this to the other side, this right here would be the acceleration. This right here would be the time. And then so this rise that I'm looking for would be the change in speed. See, and that's the equation here. But again, I think this problem is just really kind of just going all the way back to the fundamentals of graphing. Okay. So I don't need to call it acceleration times time equals change in velocity, although that's true, and I will do that in part 2. But let me just stick to what I think is kind of the first approach, and that is let's solve this just by a graph and the area under the curve. Okay, so this is 1.49 times 1.92. And so this change in speed, this rise, if you will, so I don't know if you want to call it change in speed or if you want to call it the rise, but it looks like it's 2.86. And up here in the graph, I'll put 2.86. Okay, now I'm going to need another page here. Because as I was trying to convey in what I'll call solution number 1, is that this area under the curve is the total distance she moves. And it says the sprinter runs a total distance of 35.4 meters. Okay? So let's get the area. And there's, 3 shapes here. And so maybe I'll say this, area 1 plus area 2 plus area 3 is supposed to be the total area, which would be the 35.4 meters. That's, again, what I really think this problem is after. Okay, so let me start with this rectangle right here. I'll call this area 1, and it would be this height times this width. And so this would be V1 times 1.92. Okay, now area 2, let me call area 2 this little triangle up here. Okay, so the area of a triangle is 1/2 its base times its height. So 1/2, its base is the 1.92. Its height is what we worked out, the 2.86. Okay, so that's area 2. Now, let's call this area 3. And it's a rectangle, so it would be its width and its length, or however you want to label it, length and width. But it would be the 2.95 times this height. Now, let me not call it V2, although that would work just fine. But I don't want to introduce a second unknown because we really want one unknown in one equation. And we already said this was 2.86 higher. So its height would actually be then V1 plus 2.86. And that's going to equal then the 35.4. So this first one would be 1.92 V1. This second one, let me grab my calculator, 1/2 times 1.92 times 2.86. And then this would be 2.75. Here I can do a distributive property, so this would be 2.95 times V1. And then the 2.95 times 2.86 comes out to be 8 point, and I'll just call it 4. And then all of that has to be 35.4. Now, if I put my like terms together, the 1.92, and I add that to the 2.95, this would be 4.87 V1. and equal. I'll just go to equals because these other two are just numbers I'll bring to the other side. So this would be the 35.4, and I'll subtract off then the 8.44. Also subtract off the 2.75, and that should be then the 24.21. So I get one of the two answers right here by taking that 24.21 and dividing it by 4.87. And V1 then is 4.97, which then remember V2, which is kind of how we got this number right there, is the V1 plus the increase. So this would be the 4.97 plus the 2.86. So taking that number and adding 2.86 gives me a 7.83 for V2. So there's V2 and there's V1. Okay? Now, for me to kind of actually confirm if I did this right or not, and use this as an opportunity to show you that we could probably do all of these without the graph, just with some numbers here, is to use those equations about our kinematics. So the thing to remember is we have this one equation that says final speed is equal to initial speed and acceleration times time. That's what we call the equation 1. And we have the second equation that says the final position is equal to initial position plus initial velocity times time plus 1/2 acceleration time squared. And that would be equation 2. So let's see if I can use these two equations. But this would also give me a chance to remind you that these equations are only valid for constant accelerations. And of course, back here in the graph, we said, well, do we have a constant acceleration? And not really, because she accelerates at a constant for a little bit, actually 1.92 seconds. But then her acceleration changes to 0 for the rest of the race, which is 2.95. So there is not a constant acceleration for the whole problem. But there is a constant acceleration in the two parts. So if we think about this as part 1, and this one here as part 2, then we can say maybe something like this. Maybe we can apply these equations during the time she has a constant acceleration. And so we can apply it throughout her part 1. And then whatever is at the end of part 1 now becomes the beginning of part 2. So then we can do a constant acceleration for part 2. So problems like this, when I do the math, I like to split my paper in half and say, all right, so I'm going to do part 1. And part 1 has a constant acceleration of 1.49. I'm also going to do a part 2, and part 2 has a constant acceleration of 0. And so this will justify using these equations. Notice I would never, ever, ever, ever use this equation for the whole problem, because the whole problem does not have a constant acceleration. But pieces of it do. And you could have, a third piece or a fourth piece, and each little piece has a constant acceleration. Like you could have a truck that takes off real quick with one acceleration, then hits a cruising speed and has another acceleration. Probably 0 because it just keeps going at that same cruising speed. And then they apply the brakes, and so they have another acceleration as they slow down. So I'd have a part 1, a part 2, and a part 3. And so that's a good strategy to keep in mind here. All right, so here's what I'm going to do, is I'm going to apply this equation number 2. I'll just write it down here. To part 1. And it would look something like this. The final position at the end of part 2 is not known. So let me just call it final position at the end of part 1. And so I'll just call it X final number 1. Because we have no idea where this is. We weren't given that information. Okay. But I'll call her starting position 0. Her starting speed is the V1. They made that very clear. And they also made it very clear that she does this starting speed for a time of 1.92 seconds. And of course, they also make it very clear that her acceleration is 1.49. Didn't give myself enough room for the 1.92 seconds squared. So again, just thinking about her first part and just doing numbers, not doing graph, I would say her final position, okay, would be equal to, and I've got this 1.92 V1 plus, and then this is just some number. Okay, so let me find out what that number is. 1/2 times 1.49 times 1.92 squared. And that would be a 2.74. Okay, so that's probably about as much as I really can do here. Well, actually, I could do a little more, and I'm going to need it now that I look at it. But let me justify why I need it when I get over to part 2. So if I do the same logic in part 2, I could do this. In part 2, I'm going to apply that same equation. So I'm going to write final position of number 2 is equal to the initial position in part 2. I guess I don't need to put a part 2 here because I'm in this column. Okay. But I did it here for clarity. Okay, but initial position. But remember, this means initial position in part 2. And that's a big important step because the final position of part 1 is what's going to go right there. It's going to be the initial position. So where part 1 ends is where part 2 begins. Okay, so then this is going to be the initial speed multiplied by time, and then 1/2 acceleration time squared. All right, now I'll start filling this in what I know. For example, the final position in part 2, well, that we do know. That's her complete race. At the end of part 2, she has gone that total distance, and I forgot what it was. Oh, here it is, the 35.4. Okay, so this right here is the 35.4. Now, what I'm going to call her starting position of part 2 is where she ended in part 1. So this is 1.92 times speed 1 plus 2.74. So these two together is that. Where is she? What is her starting position for part 2? It's the ending position of part 1. Okay. Now, go on to the next term, which is her initial speed. Now, remember, this is her initial speed for part 2. So that would be the final speed of part 1. And I haven't done that one, and so let me move that equation down here. Final speed is equal to initial speed plus acceleration times time. Now, I'm back into column 1. So her initial speed for part 1 is V1. Her acceleration in part 1 is 1.49. And her time, well, here's 1.49. Her time, back here in the graph, is the 1.92. Okay. So 1.92. So this becomes speed 1 plus, I'm going to grab my calculator, 1.49 times 1.92. And this is the 2.86. Which by the way, if you remember, back here in part 1, that's what we did. We said speed number 2 would be her initial speed, this height, plus this rise. And so that would be 2.86. So not a surprise, given that we already solved it doing the graphical method. Okay, so let me put this in. So this would be V1 plus 2.86 for her initial speed in part 2. And I'll say it again. Initial speed in part 2 is final speed in part 1. And so that's how we're going to justify using equations of constant acceleration. And so let me just say it again. You could only use these equations for constant acceleration. That's why we couldn't use those equations for the whole problem. But we can break it into 2 parts, where the ending of part 1 becomes the beginning of part 2. So the final position of part 1 becomes the initial position of part 2. And the final speed in part 1 becomes the initial speed in part 2. All right, well, let me continue on. So the time in part 2 is the 2.95. And I kind of ran out of room on the edge of my paper, but maybe that's good because the last term right here is plus 0, because in part 2, her acceleration is 0. Okay. And so let's solve it. So here's 35.4. This is 1.92 V1 plus 2.75. I'll leave that alone. But here I'll do the distributive property. 2.95 V1 plus, and this is the 2.86 times 2.95. And so this is the 8.44. And right here, I'll take the 35.4 and subtract off that number, 2.74. And I will subtract off that number, 8.44. And so I'm left with a 24.22. And then these two like terms can be combined, 1.92 plus 2.95, and that's 4.87 V1. And so V1 is the 24.22 divided by 4.87, and I get 4.97 for V1. And if I use that back over to here to get the final speed at the end of number 1, which is the V2, then I can take that, 4.97 and add to it 1.49 times 1.92 and get 7.83. And I believe those are the same numbers, yeah, we got up here. Good. And it's really the same math from here down. You can kind of see the same math as the area under the curve. These actually end up being the same mathematics here. Not a surprise. But I did this one, of course, looking at the graph, and this one kind of looking at these constant acceleration ones. And I think it's important that you see both of them and know both of them, although the impression I get from this problem was to focus really on the area, and I thought hopefully by me expanding, although it made the video kind of long, now I'm at 29 minutes, so hopefully I haven't lost your attention by now. But there's some neat lessons and details to learn here. All right, well, there's more I could say, but I better just stop. That's enough for now and let you digest that for a while.